Hello everybody, and welcome to section 2. We're going to be talking about evidence supporting the plate tectonic model using Pangea. First, we're going to talk about briefly here. We can see we have our continent here on the left and our ocean here in the middle and on the right. And what we're looking at, this is North America, this is Africa, and here we have everything that is in between. So the edge of the land here is not actually the very edge of the continent. Instead, the continent extends out all the way to this, what we would call the beginning of the continental slope or continental rise. See the little purple marker there at the end. So continental crust, by and large, is going to be lighter material than the oceanic crust, so it's going to sit up just a little bit higher, as opposed to the ocean crust, which is denser, going to sink down a little bit lower. But here at the boundary, we're not going to see something that's like a hard right-angle division. Instead, we're going to see something that is worn down into kind of more of a gradual slope. This that we're looking at in the middle, the mid-ocean ridge, we will cover in a little bit, but this is kind of a good diagram to be aware of generally. So here, just make it a little easier to see the outline of the continent in red. So back to Wegener and his idea of continental drift. What was part of the evidence for that? So any child who's ever looked at a world map would probably tell you, well, it looks like this piece here, South America, and this piece for here, Africa, they kind of fit together really well, actually. It looks like this, extending outward, we have Brazil, fit nicely into Western Africa over here. And it turns out that when we do this and we include the information from our last slide, not just on the land itself, but also including the shelves, they fit together very, very, very well, with only a couple regions here where we have misfit overlapping. See here, drawing attention to the continental shelves on the bottom, it actually makes a big difference down here, extending these as opposed to just the land. So another part of this, if we look at the ages of the rocks themselves, and actually we find that the ages of the rocks on either side of these boundaries are pretty well close to each other. And the ages on either side here match up pretty well. The ages on either side here match up pretty well. And this is just further evidence to support the idea that these two continents were at some point in time in the same place. And just a little detail on this one, of course, back when Wegener was proposing this, we didn't have exact ages for these rocks. So we didn't know that it was 550 million years or older than 550 million years, but we did know the relative ages of the different rocks units involved here. And you can actually see it here with North America. So the northern tip of Appalachia actually is something which contains very, very similar rocks to what's in Scotland here in Europe. Very, very similar things. So what if we put these two together? Does anything else fit? Turns out absolutely yes, it does. And by matching continents which are separated now by oceans this way, we can get sort of an idea of what this combined landmass might have looked like. Another part of it, some of the most convincing evidence is the fossil evidence. So there is this tree that we have found, the fossil leaves of Glossopteris. And this, what we're looking at over here, is actually in the southern hemisphere, towards what would have been the South Pole then. And we can see that Glossopteris is spread out throughout the entire South Pole across all these different continents, which nowadays are spread out far. Now, it makes more sense that these continents would have been together at one time than for this tree to have somehow crossed the ocean and gone to these different continents. Talked about this in the last lecture just a little bit, the Mesosaurus. So we have this rather small reptile, it's about 3 feet, which seems to have crossed an entire ocean going from one continent to another. There's also a freshwater reptile, so this becomes incredibly unlikely. The more likely explanation seems to be that these two continents at one point were touching each other, putting this and this together. And here we have just a little bit a summary of some of the fossil evidence here, looking at the southern part of the supercontinent. And something very interesting as well is glaciation. So if we look at this photo here, not the cracks here, but these little lines, like the little scratches that you see. So we've called these glacial striations. These are evidence that a glacier was here scraping against the surface of this rock. And it turns out there's evidence of recent glaciation in all sorts of different parts of the world where you do not see glaciers today, right? Everywhere from uh, India to Central Africa, southern part of Brazil, places where glaciers are not now and were not recently, but they all have these glacial striations on the rocks, telling us that at some point in the past, uh, everything we see on this map was fitted together into one landmass. And we can actually see what this landmass might have looked like here. Notice, even though this is marked North Pole, um, we're actually looking at what would have been the geographic South Pole. And we'll talk about why this is marked North Pole in a future lecture. So, just to sum up, our evidence of Pangaea, everything from the shapes of the continents, the geometry of them, to the ages of the rocks on either sides of various oceans, to fossils, to glacial evidence, it all seems to point in the same direction. It points towards a single landmass, which might have united all these continents at one point in the distant past. Um, yes, but there's, of course, a part missing. So, what is it that drove these continents apart? What is it that might have driven them together in the first place? What is the bulldozer here that's making these enormous things move? And, well, first we're going to cover a little bit on what we look at when we look at the ocean floor. So, back on World War II, there was a tremendous incentive for the military to be able to find submarines, to be able to find enemy submarines. And as part of this, military developed very, very sensitive little magnetometers, little devices which can measure magnetic signals coming up off the ocean floor. And you can imagine a small to medium-sized vessel dragging this thing across the ocean floor and keeping track of the magnetic signals that it gets. And post-war, somebody put all of this information together and figured out that it's actually something which is symmetrical along these ridges in the middle of the ocean. So the pattern that we see on one side is mirrored on the other side. And it turns out this is actually more evidence that the land masses on either side of that ocean were once together. And then, as they split apart, they rift apart, we can see all the evidence of what has happened since then mirrored on two sides of the mid-ocean ridge. And the geology here is fascinating, but one thing that you do need to know about it is that this is where new ocean crust forms, right here in the middle. So we have the pulling apart of two land masses, and this causes this deficit in pressure down underneath where they're pulling apart. Then material rises up, and as it rises up, it melts, and out comes fresh, new ocean crust. We can also look today with GPS in order to tell the absolute motion of the plates. And this is very interesting because even if somebody had no idea where earthquakes were in the world, absolutely no idea, if you showed them this map with all the relative motions put on it, and they saw, well, this part of the world is moving this direction, and this part of the world is moving here, probably something really nasty has to happen in between them. And sure enough, this is where we find a tremendous amount of seismic activity in the western United States. But through GPS, we don't just get to look at relative plate motions, which is what we had looked at up until we had these very sensitive communication satellites, but now we get to look at absolute motions. We get to look at not just one moving to the left, but maybe the other one's moving to the right. Instead, we can say with absolute certainty this one is moving west at 4 centimeters per year. Very, very useful. So putting it all together, between the shapes of the different continents, the geometry putting them together, to the geology of the rock units on either side of the oceans, the fossil evidence, glaciation evidence, and the measurements that we have of how the plates move, and through GPS exactly how the plates move. We have a pretty good idea of what this landmass Pangaea would have looked like and about how long ago it would have been around. We have all this evidence that we can put together in order to map a complete tectonic history of the Earth. So not just how things are now and how things were a really long time ago, but we can also map out all of the things that might have happened in between. And here we have just a little bit of an overview of different supercontinents. And we're not going to talk a whole lot about these. You can see on the left, Rodinia, going back to about 1 billion years, Pannotia, a supercontinent that we thought might have existed about 600 to 550 million years ago, and Pangaea, the one we're talking about. And just including some nice close-ups here, it really is amazing what they can put together nowadays for each of these. Again, Rodinia, about 1 billion years ago, Pannotia, about 500 million years ago, 500-ish million years, and Pangaea, about 300 million to about 150 million years ago. And these videos you might find helpful, different way of explaining some of the things we've covered in this lecture. There is a science history battle rap, there's an Alfred Wegener song, and bottom link here, continental drift through 3.3 billion years, is actually taking you through what I was talking about a moment ago, where we don't just talk about what it's like now and what it was like extremely long time ago, but there's also every single point in between. And I think that one actually plays it from the distant past all the way to where we are now, kind of giving you a full movie of the play-by-play of what's happened for Earth's history. Next section is going to be on the driving mechanisms for plate tectonics.